via dicendo. Ok, sì, comunque le slide le ho numerate, quindi dovrebbe essere facile piazzarci.
Io sì, certo.
Non sento le domande che eventualmente saranno fatte perché chiaramente bisogna essere al telefonino.
Vabbè, se ci saranno domande urgenti e che non si possono rimandare, sposteremo il telefonino
Esatto,
o te lo ripeto io. Insomma. Allora, la cosa divertente è alla voce ubriaco Gabriele, cosa mi streaming? Streaming alla fine, no? Non giustificato. Esatto, non giustificato. Marco Nicola, Sina, Eleonora e ok. Sentiamo Sina che... Cosa? Ah, Nicola. Sì. Okay, so everybody's here. I think we can start. So today the first speaker is Gabriele. As you can see, Gabriele is not here. He's by remote, and we will try to work this out. So pay attention and be patient, please. So Gabriele, you can start.
Thank you. Good afternoon. Today I talk about the detection of a millimeter flare from Proxima Centauri following my last journal club. Meredith McGregor take with the other authors the same data from the slide 1 from the previous observation campaign of Proxima Centauri and recalculated some things. The low mass stars are the most common star in the galaxy, and they are energy and have high frequency of Earth-sized planets in habitable zone, and also have stellar luminosity variation and high stellar activity. These consequences are astrobiological debate if planets around M-dwarf stars may developing and sustaining life. The case of Proxima Centauri is interesting because it's an M5 star, have a Earth mass planet within the habitable zone. In 2017, it discovers a new candidate in transit event, maybe a lowest density small planet. This is a flare star, and its variability affected the properties of this planet. Next slide, number 3. The observation coming from the ALMA 12-meter array and Atacama compact array at 215 gigahertz. The observation is the same as Atlanta in 2017 from January to April in 2017. There are 15 observations with the 2 scheduling blocks for 12-meter array and 15 scheduling blocks for Atacama compact array. The difference from this setup is the dimension or the diameter of the parabola. The integration time is 6 minutes with the alternating with the phase calibrator. And as the absolute flux calibration coming from Ganymede, observation from Ganymede, Callisto, Titan, and the other sources. This following the bandpass, the weather condition in the observation, and the correlation time with the spectral windows. The package for all radioastronomical data analysis used is CASA. The next slide, number 4. The first reason for the only 2 observation with ALMA is shown in the image. The leftmost image is the merging of all data set, and the natural wedge image is combined, is representative for synthesized beam from 1 arcsecond square beam. The central image and the left-right image is the single data set for the 2 observation. In the right, from the scale from 6 minus decay. This is the light curve for the detected point source fitting over the both observation. The solid black line and the shaded gray region indicate the flux density around 1000 microjansky. Is this pretty the same from the value obtained from Aglanda? The millimeter emission is clearly detected from Proxima Centauri with evidence of minor variability. The range of the emission coming from 50 to 116 microjansky. In this observation, the fractional linear polarization index Q over I is rated 0. It is a lower limit for the polarization, and the spectral index alpha is 2.5. This indicates a black body emission in the Rayleigh-Jeans regime, as expected for a quiescent stellar photosphere. The next. In this slide, we see the all 13 observation from Atacama compact array. The resolution is more high respect the ALMA, with a beam size of 7 per 5 seconds. There are an important thing to see. In image A, there are all image merged, all observation, and is detected an unresolved point source with the flux density of 300 microjansky, in agreement with the value of from Aglanda. But if you use only the first 12 images, no source is the panel B, no source above 3 sigma were detected in any of this data set. And the center peak is 32 sigma and similar to a point source. 32 is over only 2 sigma, and the point source instrumental detection limit is 3 sigma, 16 microjansky to 100 microjansky. Only in the last data set image in 24 March, there are a very big flare and a very big detection. Next slide, 96. In the observation of the 24 March, with a scan of 6 minutes and a fit mode every 2 seconds, is see in the left panel, in the left plot, the light curve of this event. The flux density is 9 sigma over the background. In the right, you see this, a similar flare, but from the microvariability and oscillation star microsatellites in white light. When these two plots show in the left the flare from the radio, and the right the flare, not the same flare, but a similar flare from the white light. The peak brightness of the radio emission have a flux density reach 100 millijansky, or a luminosity of 2 times 10 to 14 erg per second per S. A factor nearly 1,000 times brighter than during quiescent as measured in the ALMA 12-meter observation. The complete transit event lasts approximately 1 minute. Next slide. This is the comparison from in the plot above the flux density over the time, and below in the center the spectral index, and in the bottom the polarization during this transient. During the flare, the spectral index becomes negative in the center, with a minimum value of alpha around minus 1.7. And during initial steep rise in flux density, the lower luminosity on the fractional linear polarization given negative. At the peak, the sign flipped to positive value before returning to 0 at the flux density decline. But alpha and the polarization index differ significantly from the quiescent value determined for the ALMA observation by over 5 sigma, indicating a change in the source emission during a flaring event. The origin of this change is now unclear, may be attributed to either plasma emission or electrocyclotron mass emission. The next slide. The author discusses the nature of this detected flare. In Proxima Centauri is known to undergo frequent X-ray flare. For example, the rate of one large event, 10 times quiescent level above, is every few days, or the XM Newton causes a large X-flare with a luminosity, a total X-ray energy of 10 to 32 Hertz, lasts for 10 minutes. In the visual wavelength, flare occur at a similar rate for several per day. By extrapolating flare energy frequency and distribution, Proxima Centauri might display about 8 visual flares each year with energy over 10 to 33 Hertz. This is a very important thing. In the plot, okay. The discussion continued with the nature of the detected flare in the millimeter emission was also being detected in solar flare. These events are associated with extreme X-ray emission, class X5, X6, or X9, have a duration of minus and have a positive spectral index. This is for our sun. Even for the sun, the origin of this emission is unclear. Two possible emission mechanisms are investigated: the synchrotron emission from ultra-relativistic electron or extreme infrared determinant extension of the heated chromosphere. In comparison with the sun, the maximum submillimeter flux density of a solar flare have a luminosity of 2 times 10 to 15 Hertz per second per Hertz, and the spectral index is every time positive. The peak luminosity observed in Proxima Centauri is 10 to 14 Hertz per second, a factor 10 times larger. And the observed spectral index is negative, controversy with the sun. The spectral index may indicate that we are seeing the optical thin path of the gyrosynchrotron spectrum. Next, the 9 and 10. In the discussion, the author discussed about the system around the Proxima Centauri proposed by Aglanda. The system in the illustration have in the center Proxima Centauri, in orbit 1 Proxima Centauri b, the small planet Earth size. In 2, maybe a warm dust. In 3, hypothetical source. This data is extrapolated from the same data set of this paper. And other cold belt and a very other belt. But this feature coming from measure the stellar photosphere flux minus the total flux in the ACA image or in the ALMA image. The first discussion is around the warm dust. This is shown in number 2. Assuming small flare have a flat spectrum at a millimeter wavelength, this is sure overestimates its luminosity. But with a small luminosity around 50 micro Jansky, measured during this quiescent luminosity, is around 10 to 21 Erg per second, is less than 10 to -9 times the bolometric luminosity of the star. A grande detects a slight elongation of the central source along a position angle of 130 degrees, but the dataset is of an unresolved source below 2 sigma level. This is made from the UV model fit of Gaza. Compared with the other image of stars, this warm dust is plausibly explained with a weak flare emission. It's not a warm dust. The cold belt indicated by number 4, proposed by Grande, uses all images to determine its system, also with a flare event. In this case, there are no emissions detected over 3 sigma in the first 12 non-flare events, and averaging all data set, the cold belt appears exactly 300 microjoules like a Grande. In this case, the cold belt don't exist. In the other cold belt, this is detectable with 3 sigma above the ground. The aqua visibilities do not cover the short spatial frequencies to robust detect the outer disk. And each peak has a flux density around 100 to 200 microjoules. It is compatible with faint background source. In this case, the extended distance is difficult to detect. The last, this is the conclusion. Ok, grazie.
We can switch to the second speaker. We need 2 minutes because we have to change the settings. Martina? No, arriva Martina, sto aspettando l'aiuto tecnico. Lui, non so, perché non so, sì, penso si possa staccare. Gabriele, sei ancora in linea? No, ha tirato giù.
No, ci sei? Stacca pure il jack. Pronto? Ehi. Sì.
No, sono passati 15 minuti e lo speaker ha il compito di far mantenere, no? Di rimanere dentro ai tempi. Quando di solito si rinva fuori dai tempi, no? Si dice.
Sì, era un po' disturbato l'audio, poi tutto a posto.
Si sentiva.
Ok.
Okay, so we are ready for the second speaker, Piero, and he will talk to us about the semi-galaxy survey spatially resolving the main sequence of star formation. Please.
Good afternoon, everyone. This will be a longer presentation, so you can go if you want. Sorry. Okay. The stellar masses and star formation rates of star-forming galaxies follow a direct relation called the star-forming main sequence. This relation is pretty simple. It is a power law. The star formation rate is proportional to the stellar mass to the power of beta, where beta varies from 0.7 to 1 in the literature. This means that the specific star formation rate, which is defined as the ratio of the star formation rate and the stellar mass, is nearly constant in a given redshift bin. Star-burst galaxies, which have an enhanced star formation rate, lie above the main sequence. Instead, the quenched galaxies lie below the main sequence. Traditionally, the integrated star formation rate and the total stellar mass of galaxies are used. But integral field spectroscopy surveys allow us to study how the star formation rate varies inside each galaxy. The authors used the SAMI survey data, which is an integral field spectroscopy survey. The catalog contains more than 1,200 galaxies with redshift lower than 0.1. Okay, here you can see sum of the derived quantities from the SAMI data for the galaxy gamma 31452. Okay, star formation rates are measured through the age alpha emission after extinction correction via Balmer decrement. Here you can see the age alpha flux map, and the attenuation correction map. There are also the nitrogen 2 and the sulfur 2 emission maps that together with the oxygen 3 and the H beta emissions are used to build these three diagnostic diagrams. These diagnostic diagrams are useful in order to distinguish between the age alpha emission due to H2 regions and the age alpha emission due to other sources, AGNs typically. A pixel is considered star-forming dominant if line ratios with a signal-to-noise ratio high enough lie in the right regions of the diagnostic diagrams. Then you construct a star formation mask to select only the star-forming pixels. But how is the star formation rate map constructed? Well, you have to multiply the age alpha map by the attenuation correction map and also by the star formation mask. Then you use the result together with the galaxy distance to compute the intrinsic luminosity of the emission. And the intrinsic luminosity is proportional to the star formation rate. So in this way, you can generate this map of the star formation rate surface density. The authors used for the galaxy contained also in the Gamma catalog, Gamma is another survey, used also optical and near-infrared images to generate the stellar mass surface density. For each pixel, they performed a fit with a stellar population synthesis model, and they derived the stellar mass surface density, and so this map. The authors used also the environmental density measurements from Gamma, defined in this way, where D5 is simply the fifth nearest neighbor distance. Well, so let's study the galaxy population properties inside the SAMI galaxy, the SAMI survey, sorry. We begin with the traditional plot I have just shown you, where the integrated star formation rate is plotted against the stellar mass. Here galaxies are color-coded according to their morphological type. And we see that star-forming galaxies follow a relation that is in good agreement with relations found in our work. Well, let's move instead to this other plot, where the galaxies are color-coded according to the environmental densities. We see that at higher masses, it doesn't matter if the environmental density is high or low. There are, for example, star-forming galaxies both in dense and dilute environments. Instead, at lower masses, quenched galaxies are found only in dense environments. But let's study deeper these properties by using integral field spectroscopy. So let's let's study how star formation rate varies inside the single galaxies. In this figure, you can see the radial profiles of the star formation rate surface density. The profiles are grouped in 4 bins of mass, the columns, and in 5 bins of vertical distance from the main sequence fit, which is this line here. Okay, the thin lines are the single profiles, and their colors represent the morphological type. Thick lines instead are simply the median profiles. So we see that increasing mass, the star formation rate levels increase and decrease going farther from the main sequence. We can see also that within 3 sigma from the main sequence, the radial profiles are centrally concentrated, and below they are flat, more or less. We see that the star formation rate levels decrease going forward, but decrease especially in the central regions. So this suggests the presence of an inside-out quenching mechanism. You can see also that in each bin, more or less, there is a considerable scatter, both in the star formation rate levels and in the shape of the radial profiles. This means that starburst galaxies are not necessarily galaxies with an enhanced nuclear star formation rate. The star formation rate could be enhanced also in the outskirts of these galaxies. Here there is a radial profile that goes in the opposite direction. Okay. Now let us investigate the causes of quenching. Mi spiace. You can go if you want. So the authors tried to understand first the impact of morphology, and they plotted for each pixel the star formation rate surface density against the stellar mass surface density in 5 bins according to the morphological type. And you see that at any morphological type there are pixels and so regions in galaxies close to the main sequence fit, the solid line. In order to understand better what is going on, the authors plotted also the radial profiles of the specific star formation rate and of the star formation rate surface density. Thick lines are the median radial profiles for all the morphologies. They are simply copied in each panel along each row. So you can see that elliptical galaxies more or less have lower specific star formation rates, especially in the center, where it is particularly suppressed. It is another proof of inside-out quenching mechanism. But the underlying contours for early type galaxies put in evidence the presence of two subpopulations. One star-forming, the upper, and the other quenched. The upper one show radial profiles similar to late type spirals profiles. The other instead is completely different. Okay. So morphological differences do not determine whether early type galaxies fall on or below the global star-forming main sequence, because we have elliptical galaxies both on the main sequence star-forming and also below the main sequence, quenched elliptical galaxies. So the authors considered other possible drivers, in particular stellar mass, environment density, and central stellar mass surface density, but they found no statistical significant difference between upper and lower populations. Okay, the striking differences between the upper and the lower populations in early type galaxies suggest that the presence of a massive bulge is not sufficient to quench galaxies, as someone argued, because of there are elliptical galaxies with massive bulges that continue star-forming stars as late-type spirals. So there should be another quenching mechanism in act. Okay, so let's try to understand the impact of environment. These are the same process before, but they are binned according to the environmental density. And here the two subpopulations are not clearly disentangled as before. In fact, at any environmental density, galaxies have regions close to the main sequence. For example, if at even higher density, if we take the galaxies with pixels in this region, we see that the same galaxies have also pixels and so regions close to the star-forming main sequence. But there are other interesting things here. For example, in dense environments, the gradient of the star formation rate profile is steeper and in the nuclear regions. And this is the proof of the presence of run pressure stripping. In dense environments, there could be also strangulation type processes, but the strangulation type processes affect all the regions of the galaxies. And we see that the star formation rate is suppressed, especially in the outskirts. So the authors think that the run pressure stripping is the dominant mechanism. And finally, so far we have seen the analysis in a given bin of mass, because the authors wanted to get rid of any possible mass effect. Now we study how the radial profiles vary with mass, and keeping fixed the environmental density and the morphological type. The upper panels are for the late type spirals, and we see that radial profiles of specific star formation rates do not vary so much with mass. The star formation rate increases with mass. So this means that halo quenching, which is a strangulation type mechanism, if occurs for late type spirals, then it must occur at masses even higher than those considered in this sample. Instead, for early type galaxies, the specific star formation rate levels decrease with mass, but the star formation rate is not so much. So halo quenching could be occurring, but it is not sure. Okay, so let's summarize the results. Below 10 to the 10 solar masses, only galaxies in medium to dense environments fall below the star-forming main sequence. Only 3 sigma or more below the main sequence, almost all galaxies show flat star-formation rate surface density profiles. Early type galaxies split into two populations, one star-forming and the other quenched, with different star formation behaviors, one on the global star-forming main sequence and one below. The two early type populations have statistically similar stellar masses and central stellar mass surface densities, showing that neither halo quenching nor bulge formation are independently sufficient to produce the split. So quenching probably is due to a combination of these two quenching mechanisms. And galaxies in dense environments have overall lower star formation rates. And this is the case most pronounced in the outskirts of those galaxies, because interaction and pressure stripping are the probable causes.
thanks, Piero. We technically have no time for questions, but if you have questions.
So in yearly types, also DH alpha is used as the star formation rate tracer. So
yes.
they have emission lines in H alpha also for all yearly types.
Yes. In particular, in the star forming subpopulation of the yearly type.
So the quench population is mostly bulges rather than urellipticos.
Yes, of course, there is a mask here that select only pixels with a not negligible star formation rate.
Okay, so let's thanks Piero again. I'd like to remind you that your presentation should be or have to be 10 minutes long. No more, no less. This is a test bench for your future conferences. As I'm the chairman, and chairman do not give you more time than you should have. So if you have 10 minutes, you have 10 minutes. So please remind that for your next presentation, and thank you again.